Hi, welcome to another episode of Mr. Avila Physics. Today we're going to be talking about free falling motion. Now, we have all dropped something from above and we realize that when that object falls through the air, the object picks up speed, starts going faster and faster. So, if its speed is changing, then its velocity is changing. So that means that as objects fall through the air, they accelerate. Now, this was first noticed by Galileo when he did his famous Pisa Tower experiment, where he went to different spots in the Pisa Tower, dropped objects of different masses, and realized that they landed pretty much at the same time. The conclusion from that experiment was that at a given location on the Earth and in the absence of air resistance, all objects fall with the same constant acceleration. Now, this acceleration is the acceleration due to the gravity of Earth. And this acceleration has a magnitude of 9.8 meters per second squared, and it always acts in the direction towards the center of the Earth, so downwards. So, if we take different objects and we drop them from a certain height, then as they fall, they accelerate, which means that the distance covered with each successive second increases. So for instance, after 1 second, the bolt or the object has fallen a distance of 4.2 meters, and after 2 seconds, it has fallen a distance of 19.6 meters. So in the second, it fell more than 4.9. And in the third second, it fell more than 19.6. So the distance with each consecutive second increases, which means that the object accelerates. Now, since this acceleration is always constant, and we learned in a previous video that in order to use the kinematic equations, acceleration has to be constant, then that means that we can use the kinematic equations to analyze free falling problems, as long as we make very small modifications. So let's look at our equations for free fall. Now, our final velocity, Vf, is the same, right? So Vf would be final velocity. Vi would mean initial velocity. But now, instead of A, we have G, which is the acceleration due to gravity. And it has a magnitude of 9.8 meters per second squared downwards. And T is time. The other equations are the same, right? We have this one with a small modification that now distance or displacement is measured vertically. So y would be equal to the vertical distance or displacement. Okay. We have our other formulas. Okay, Bf squared is equal to Bi squared plus 2Gy, and our average velocity formula. So these four equations are the same equations that we use for kinematic motions, but we just make the small changes of changing d for y and a for g. Now, let's look at some examples. Estimate how long it took King Kong to fall straight down from the top of the Empire State Building and his velocity just before landing. Pause the video here, take a couple of minutes, and see if you can solve this problem. Alright, welcome back. So here we have a problem where King Kong is falling from the top of the entire Empire State Building, okay, starting with an initial velocity of 0, and he's going to fall a distance of 380 meters in a downward direction. And we want to find out how long, which is a measure of time, and we want to find his velocity just before landing, so Vf. Okay. All right. So let's look at this problem here. Now, to solve question A, I'm going to use the equation y equals bit plus 1/2 gt squared. Now, my displacement is downwards, so I gotta place a negative sign there because displacement is a vector quantity and it has magnitude and direction. So, negative 380 is equal to 0 times t plus 1/2 times negative 9.8 t squared. Acceleration also points downwards, so it has to be negative. From here, we see that negative 380 is equal to negative 4.9 t squared, which means that t is equal to, okay, take our calculator here, 380 divided by 4.9, okay, that would be, t is going to be equal to the square root of 77.55. So t is going to be equal to plus or minus 8.8. Now, since time cannot be negative, then we eliminate the negative option and we can say that time is equal to 8.8 seconds. All right. Now that we know the time, we can calculate the velocity just before landing. So I'm gonna erase this procedure and restart the problem for question B. So once again, we have our building here. We have King Kong falling a distance of 380 meters downwards. Now, to calculate his time, I'm going to go ahead and say, to calculate his velocity just before landing, I'm going to go and calculate Bf is equal to Bi plus Gt. Bf is going to be equal to 0, which is his initial velocity, plus negative 9.8, because acceleration points downwards, times time, which we just found in the previous example, 8.8. So that means that my final velocity is going to be equal to 8.8 times 9.8 gives me 86.24, negative 86.24 meters per second. And this negative sign makes sense because this negative sign tells me that the King Kong is moving in a downwards direction. All right, let's look at another example. In this example, we have a baseball that is hit almost straight up, so we will assume that is going vertical with a speed of 25 meters per second. Estimate how high it goes, how long it is in the air, and what factors make this an estimate. So, okay. We have a baseball bat here, the ball is hit, it goes straight up and then comes back down. Now, something very important happens in free-falling motion when an object reaches its maximum point. So when an object reaches this maximum point right here, the object stops for an instant before starting to come back down. Okay, so the object starts with a certain velocity. It goes up. When it reaches this top, the velocity is 0. And then it starts to come down. And once it reaches the same height, then the velocity has the same magnitude as the initial velocity, but in different directions. Okay, so let's see if you can use this new information to solve this example. So pause the video here, take a couple of minutes, use this new information and see if you can come up with an answer for this. All right, welcome back. So let's look at this problem again. So we have the baseball bat, hits the ball goes straight up, reaches the maximum point, and then comes back down. So the first question is asking us to estimate this distance right here. So to estimate distance without time, right, because I don't have any information about time, I'm going to use this formula. So bf squared is equal to bi squared plus 2gy. My final velocity is 0 because it reaches the very top and the ball stops for an instant. Then this is going to be equal to 25 squared, positive 25 because it's moving upwards, right, plus 2 times negative 9.8 times y. So negative 25 squared divided by negative 19.6 is equal to y. Y is equal to positive 25 squared divided by 19.6, 31.88. So the ball reached a height of 31.88 meters. This answer is positive, which makes sense because the displacement of the ball is in an upward direction. Alright, now let's find out how long it is in the air. So I'm going to go ahead and use this formula. Bf is equal to Bi plus Gt. Final velocity is negative 25 meters per second because when the ball reaches the same initial height from where it started from, the velocity has the same magnitude but opposite direction. So this would make it negative 25. It's equal to an initial velocity of positive 25 plus negative 9.8 t. So minus 50 is equal to negative 9.8 t. Time is equal to 50 divided by 9.8 is equal to 5.1 seconds. So it took the ball 5.1 seconds to reach the top and come back down. Now there's another way that we can solve this example, right? I could say Bf is equal to Bi plus Gt. I could say final velocity is 0, initial velocity is 25 plus negative 9.8 t. When I solve this, I get negative 25 is equal to negative 9.8 t, which means that t is equal to 25 divided by 9.8, which is 2.55. But this is the time it takes to reach the maximum height. The ball still needs to come down, so I multiply this by 2 and I get 5.1 seconds as a total time. So, two different ways of solving this problem. And what factors make this an estimate? Well, one very important factor that makes this an estimate is the word almost straight up, right? So it's not completely vertical, but it's almost completely vertical. So there's an estimate there, right? Another factor that makes this an estimate is we are ignoring the height of the player here, right? Because the ball lands here on the ground, so we are ignoring this extra distance that the ball lands. Okay, so, and we're also ignoring air resistance. So a couple of a few things that make this an estimate. All right, let's look at this other example. Roger sees water balloons fall past his window. he notices that each balloon strikes the sidewalk 0.83 seconds after passing his window. Roger's room is on the 3rd floor, 15 meters above the sidewalk. How fast are the balloons traveling when they pass Roger's window? Assuming the balloons are being released from rest, from what floor are they being released? Pause the video here, take a couple of minutes and see if you can answer this example. All right, welcome back. So here we have Roger's window, okay, right here, and the balloons pass through this window right here, going at a certain velocity, and then they reach the ground, okay, they reach the ground sometime later, here, 0.83 seconds later. And this distance is, of course, 15 meters. All right, so let's see how fast the balloons are going here. So I'm gonna take this velocity that I do not know as the initial velocity. So initial velocity okay, I'm going to take this as the initial velocity and I'm going to use the equation y equals bit plus 1/2 gt squared. Now from here I can say that y is -15, right? Because the balloons end up 15 meters below where they started from. And this is equal to 0.83 times pi plus 1/2 times -9.8 times 0.83 squared. Right? From here I can solve for vi, and vi is equal to -15 plus 0.5 times 9.8 times 0.83 squared divided by 0.83. That gives me a velocity of -14 meters per second. So how fast are the balloons traveling? Remember, how fast is a measure of magnitude. So it doesn't matter the sign, so the final answer should be positive 14 meters per second. All right. Now, for the second part of this problem, right, we assume that the balloons are being released from rest. Rest means an initial velocity of 0 from a certain height, and then they reach a velocity of 14. So I'm gonna figure out what distance the balloons traveled before reaching a velocity of 14. So final velocity is -14 squared. Initial velocity is 0 because they are released from rest. And this is 2 times -9.8 times y. So here I get -14 squared divided by -19.6 gives me -10. So -10 equals y. This means that the balloons traveled 10 meters downward before reaching Roger's room. So that means that they were thrown from a distance of 10 meters above Roger's room. So that would be a total height of 25 meters from the floor. And if each floor is 5 meters high, then 25 divided by 5, that puts us in the 5th floor. So the balloons were thrown from the 5th floor. Hopefully this example makes sense. And now you are ready to use the kinematic equations to analyze free falling motion. Alright, next thing we're going to talk about is air resistance and terminal velocity. Now, air resistance affects everything, but the effect is usually so small that we ignore it for the most part. Okay? Now, as an object falls through the air, its speed does not increase infinitely. Okay? It will come a point where it will reach a constant value. So that means that there has to be something that kind of slows it down or stops it from accelerating further. So now we have acceleration due to gravity pointing downwards, and we have the acceleration caused by air resistance pointing upward. This means that as air resistance is increasing, the total acceleration decreasing, until there's going to come a point where the acceleration due to air resistance is equal to the acceleration due to gravity. And when that happens, the net acceleration is 0. And when the net acceleration is 0, the object stops accelerating and it moves with constant velocity. Okay? This velocity is what is known as terminal velocity. So let's say, for example, we have a whale, right, that is free falling through the air. At first, the initial velocity is 0 and the acceleration is equal to 9.8 in a downwards direction. As it moves, air resistance is increasing. Okay? So the velocity increases, g stays the same constant, and air resistance starts increasing. Eventually, there comes a point where air resistance is equal to g, acceleration is 0, v, the velocity reaches a maximum value, which is known as terminal speed. Alright, thank you for watching. I'll see you next time.